Greetings, calculus students, and welcome to this extra example video on work. Now, we've certainly done some work examples in class, but there are so many different scenarios, so many interesting examples we could do. It's going to be good to have a video on a little bit of a scenario with a little bit of a twist to it. So, for instance, in class, we did an example where we were lifting an object that was 10 pounds, but the object was always 10 pounds. To make things extra fun and extra interesting, we can suppose that the weight of the object that is being lifted is changing. And that's what we'll do in our example here of lifting a bucket out of a well. Let's see if we can get that. Okay. So the well here is 50 feet deep. So we filled the bucket with water and we begin lifting it. But here's the twist. This is a leaky bucket. So as we lift it, it is losing water. Okay, and of course it would be losing water over time. But we will relate the loss of water to the height of the bucket. We'll presume that everything is kind of proceeding at a constant rate here. So let's introduce some notation already. Again, you could introduce this on your own if it wasn't already given. We're making it a little bit easier here. So the weight of the bucket we will denote by B of H. And this includes not just the bucket itself, but the water that is in the bucket as well. We're measuring weight here in pounds. And we're relating that weight to the height H of the bucket above the bottom of the well. Okay, again, the well is 50 feet deep, but the height starts at 0 and goes up from there. And this is going to give us a function relationship. The bucket will only have one weight at a given height. And here is the information that we have about that. When we first start raising that bucket, when it's at the bottom of the well, it is all the way full of water and it weighs 20 pounds. By the time it gets to the top, it only weighs 12 pounds. It has lost 8 pounds worth of that water that was initially in it. So we will assume that the bucket loses water at a constant rate. Again, this is relative to its height throughout its journey from the bottom of the well to the top. And importantly, in this example, we are going to ignore the weight of the rope. This, of course, happens in some problems that are mathematically formulated. You only take into account certain details and you ignore others. That's what allows the mathematical problems to be simple enough to be solved typically, although we certainly could take into account the weight of the rope here and add that into our considerations. It would make things even more complicated than they will already be. And presumably this rope is a fairly thin rope, does not have a lot of weight to it anyway. Okay, so there is our scenario. The first thing we would like to do to analyze this problem and to compute the work, which is what we're trying to do here, of course, didn't come right out and say that perhaps, but we want to compute the work in raising this bucket. And the first step in that is going to be to give a formula for this function b. Now you might wonder how we can do that with the limited information we have. But the key here is that we got a constant rate at which the bucket is losing its water and hence at which its weight is decreasing. What this tells us is that the relationship is going to be linear. Linear relationships are those where the rate is constant. And so if we know, if you know 2 points on a line, then you are able to find an equation for that line, and that is exactly the approach we're going to take here to be able to find that. Okay, so if we think of ordered pairs here, h, b of h, so height as the input, weight as the output, we do have 2 bits of information here. So when the bucket is at the bottom of the well, its height is 0, and its weight at that point is 20 pounds, so 0, 20. will be a point on the graph of this function. And when it gets to the top, its height is 50 and its weight is just 12 pounds. So 12 would be the second coordinate there. Okay, well, there we go. We got 2 points on our line. We can now go ahead and find a formula for it. It's a two-stage process. First, we need to find the slope. Okay, so for the slope, typically represented by m, we can do rise over run. And our rise here is actually going to be the weights. A little different from the situation itself, but let's subtract our y values up here. 12 minus 20, that'll give us the rise. And then the corresponding run will be 50 minus 0. Okay, so that gives us a slope fractionally of -8 over 50. And depending on your preferences, you could work with this as either a fraction or as a decimal. As a fraction, it would be -4 over 25 in lowest terms. I kind of do like fractions, but maybe for this example, we will go with a decimal. So as a decimal, that is -0.16. So now from here, we can initially use point slope form. For the equation of this line, we're going to want to write it as, functions typically are at the end of the day. So what we're going to have here then is change in our y's. So that'll be b of h minus, we can pick any one of the points here. I'm going to pick 0, 20 because it's got a 0 in it. And that is going to equal slope, -0.16. times the change in the x values, which x values, of course, here we don't have x, we have h, but change in inputs, let's put it that way. This one will be h minus 0. There's that 0 that's making this a little bit easier. So to express this as functions typically are, with the output by itself on one side, we can just rearrange, add that 20 over, and we get that b of h is equal to, if I put the constant first, which I can do, makes it look a little nicer, I get 20 minus 0.16h. Okay, there we go. We have a formula for our linear function, b, representing the relationship, how the weight depends on the height for this bucket. Okay, probably we should rewrite that formula on top of the next slide, so that we have it for easy reference. Again, it was b of h. Let's see if I can get this to keep working. 20 minus 0.16h. Okay, that'll definitely come in handy as we go on here. Okay, now we have a product here to compute, which is b of 5 times delta h. And we're also given the extra piece of information that here, delta h is 2 feet. Remember, delta is calculus notation for change in, so it's a change in h of 2 feet. So b of 5 here, we could compute that perhaps to get started. So we've got our formula up there. It'll be 20 minus 0.16 times 5. And so that's 20 minus 0.8, which is 19.2. Okay, now that is a weight. B outputs of the function b are weights, and our weights here are measured in pounds, so that's going to have a unit of pounds on it. Okay, and then delta h, we already see that that is 2 feet. So b of 5 delta h, that is going to be 19.2 times 2, which is 38.4. And if you notice, we are multiplying together quantities that have units pounds and feet. And so the unit overall is going to be the product of those as well. This is in foot-pounds. So it's 38.4 foot-pounds, which kind of perhaps clues you in to an answer to that question at the end there. What might this product approximate? Well, it's approximating some amount of work. Let's see how much space I left myself here. Oh, we got plenty. Okay, so there are different interpretations that you could give to what this represents. Let me give one. So here, let's suppose that we're lifting our bucket. Okay, here's the bottom of the well where the water is. And so far we have lifted it to a height of 5. And then we're wondering what happens when we lift it 2 more feet. So this would be our delta H, which is 2. Okay, so when the bucket is at a height of 5 feet, how much work does it take to lift it 2 more feet? Okay, now you could go the other way with it and say, it starts at 3 feet and we're lifting it up to 5. But let's just stick with one interpretation here to keep things perhaps a little simpler. Okay, so we could say that this represents, or this approximates, long word, this approximates the work to lift the bucket, or in raising the bucket, from, extra letter in there, Old English, from a height of 5 feet to 7 feet. Okay. Now, you might wonder, why is this an approximation? Okay, the next question kind of gets at that. Is this approximation an overestimate or an underestimate? Well, the reason that this is an approximation, if you want to pause and think about it, you can. But it's presuming that the weight of the bucket is constant during that 2-foot lift. We know that's not the case. Okay, as the bucket goes through its journey here from a height of 5 feet to a height of 7 feet, it's going to continue losing water, so that its weight will be less during this journey than the 19.2 pounds we have presumed. Okay, so that means that the work that we computed is going to be an overestimate or an underestimate. Think about it. It'll be an overestimate, right? So it's an overestimate. Circle that. And the reason is that throughout this lift, the bucket will continue to lose water. That has one S, doesn't it? Will continue to lose water. Lose? Yeah, I think so. And hence it'll weigh less. During this 2-foot lift. Okay, and by left, again, I mean less than 19.2 pounds, which is what it weighed at the beginning of this lift, right when it was at 5 feet high, but it will continue to go down. And so it'll actually take less work to raise it than what we approximated that work to be. Okay, another one for you to try, and again, we'll not go through this one on the video, but try computing B of 22 times delta H. Here, delta H is 0.25 feet. You can see if you get 4.12 foot-pounds for that, and see if you can give an interpretation of what that particular value represents as well. Now, we're going to want to generalize. And so let's get to that. Okay. What about B of H times DH? Notice it's not delta H anymore, which is an increment in H by an amount such as 2 feet or 0.25 feet. The difference with DH is that it represents an infinitesimal change, an infinitely small change in the height. So what this quantity represents, and this is the one that we are going to be most interested in for our purposes, this is a differential, the differential of work. So this is the differential of work. How much is how much is the extra work that is going to be done in raising that bucket an additional DH feet? Okay, so DH additional feet when it is already at height H. How much space did I leave? Ooh. So when it is at height H feet. Okay, so this is following our procedure again of breaking things down into very small pieces, computing what's going to happen with each little piece, and then adding up those results to get the exact total. So from here, I mean, we have our differential of work in number 5. What we need to do to get the total work is just add up all those differentials of work, and we know that that is going to be represented by an integral. Okay, so we will have the integral of our differential of work, which is B of H dH. And if we think again of where are these little increments occurring of our height? Well, we have to lift that bucket ultimately all the way from the bottom of the well up to the top. We know that it is 50 feet deep, so we're starting at the bottom, which is height 0. We're going to the top, which is height 50, and we have to add up our differentials of work across that entire 50 feet worth of differentials in height. So there is our integral. Now, we already computed. Boy, this was on the previous screen. Let's see if we remember it. B of H, our weight or our force, was 20 minus 0.16 H. Okay, we have that times dH. Okay, and then at this point, again, I would say lion's share of the work is done. We just need to go ahead and evaluate this integral to get the total work. And this part, thanks to the fundamental theorem of calculus, is pretty easy. So we'll get 20h minus 0.08 h squared, and then we want to evaluate that at 0 and 50. Okay, put 50 in there. We get 20 times 50 minus 0.08 times 50 squared. All right. I should probably mention, too often we just completely ignore this part. If we do put in 0 for the height, we would get 0. 0 minus 0, so that part is indeed going to be inconsequential. Always good to check that, though. 20 times 50 we know is 1,000. Okay, and then we have to do 50 squared. That's 2,500. Okay, and that would be the same as, for the product here, the same as 8 times 25. We just rearrange our orders of magnitude there. 8 times 25 is 200. And let's see. So 1,000 minus 200. We got it to that point. And that is 800. Okay. So what this tells us then, if we want to express our final answer to how much work did it take to lift this bucket, I'm going to say the work done in raising our leaky bucket. And it is 800 foot-pounds. Again, feet is our unit of distance here, pounds is our unit of force, and so foot-pounds then is the appropriate unit to use for the work. Got E in my done there. Okay. And so essentially we are done here. Just a couple things to wrap up. Good question to ask yourself is what was varying in this particular work problem that compelled us to use an integral? And by far here, so this one, certainly what's happening is the force is varying. The force is the weight. The weight of the bucket is changing as we lift it. The incremental lifts that we're doing are all the same. They're all dH. In some of the other problems we've looked at, you could just as easily interpret either way as the force changing or the distance changing. This one here, I think really there's one clear natural interpretation, the one we just described. If you wanted to think of this as distance changing instead, you could finagle it into that by thinking about different portions of water in the bucket being lifted, different amounts. But I think that's a little trickier to envision what's going on with that. So I think really here we're looking at a force varying situation to keep things as simple as we can. Okay, I hope you enjoyed this journey with the leaky bucket, and we'll see you again soon.